Are we live? Hello, hello. Are we live? Yo, can you guys hear me? Hello, hello. My keyboard is so loud, dude. Are we live? Yo, can you guys hear me? Bro, my keyboard is so loud. Um, alright, if you guys can hear me, say something. Also, let me know if the audio is synced weird or yeah. Yeah, here we are. What's up, guys? First time doing this like ever. Okay, I'm gonna. Hey, Mont, do you know if there's gonna be like anyone else who's gonna join? Just let me know. I can wait for them before I start so that we don't get any people who are like lost. Uh, Sorry for the dirty room. Uh, Looks like a tornado swept through here. That's how things are. So, okay, just let me know if you guys want me to wait for a couple of other people to join up. In the meantime, if you don't have Fusion 360 or something like that, go ahead and check out one of my other videos. I think it was one where I talked about like how to actually download Fusion 360 and how to get an education license. But go ahead and do that. In the meantime, yeah, you guys are on the left of my screen, which is why I'm looking to the left. Sorry. Here, let me see if I can. Ooh, nice. Well, that's you guys. I'm gonna keep you over here. Okay. Yo, what's up, guys? Okay, let me know if you want me to wait for anybody you want them. Others. Okay, if not, if we're not waiting for some people, I'm gonna get set up here so that this goes as smoothly as possible. Because we're trying to be in and out of this whole tutorial thing in like roughly 2 hours. By the way, I'm just gonna preface this is kind of like a dual purpose. I'm I'm live streaming for robotic stuff, of course, but also for something I have to do for school called a CAS project. So I'm just letting you guys know what we're doing here today. Um, oh, by the way, because you guys are early, you get a sneak peek at all of our CAD. I'm just joking. I'm gonna show this to everybody, but there you go. Assembly. There we go. Let it load. Give it a sec. So, how are you guys today? Good morning, right? Just a peaceful day so far. I mean, it is, what is the holiday today? It's like Good Monday or Good Friday or something Saturday. I don't know. Some, some sort of holiday, something, at least they give us school off. Okay, let's get this goofy contraption out of the way. Let's hide. Okay, bro. You wanna hide? I'll hide you manually. DNU tournament? Yeah, no, this was not DNU tournament. This was state. DNU tournament was way earlier. I can show you that one if you want. Okay, so this was like our 6th iteration. I'm just gonna hide this too. Allergies are so bad right now, dude. I don't think you guys know. It's pretty terrible. Okay, so okay, almost ready. I'm gonna save one more design in here, here. Oh shit, what position? Here, here. All right. Well, I'm just gonna make sure everybody knows that we're out here and we're live real quick. Maybe not at everyone. Maybe like yeah, I'm gonna start from the very beginning because this is kind of meant for people who don't know much about CAD. Um, yeah, and the reason why I'm doing live is so that it's like in my YouTube channel so that members on my team can look back at it. Um, but like if you want me to skip some stuff because you guys are pretty much the only two here, but I think I'm gonna start from basics. Um, and I'm gonna start in like right now because it's 11:30. Okay, let me give it a sec so that my friend can edit it later on. Okay, starting now. Hello everybody. My name is Amity Ravali from Team 19587, and today I'm going to go through some CAD concepts and sort of a CAD tutorial for new members, and maybe you returning members or veteran CAD members might learn something new, might learn something from this tutorial. So, I'm going to start off pretty basic. We're going to start right at the beginning. I'm going to assume that you already have a Fusion 360 account, a Fusion 360 license, and the actual application, because can't really do it without that. And we're just going to go through this. So, first things first, this is your data panel. So, this data panel here basically shows every single project that you are a part of. These are all the sample projects that are given to you by Fusion 360. Um, these are your assets which you can use for materials, colors, whatever, what have you. And these are all the projects that you may be a part of. And you can just make a new project by doing this right here. Create folder level project. Now, my entire Fusion 360 is shared with my team on the team account. So if at all you have or you're not associated with a Fusion team, then you're just gonna be the only one with access to these teams or to these projects. Okay, so I'm just gonna go into how projects are organized, what all of these icons, this mess over here is, right? First things first, this is your document. This is your open workspace where you can use all these tools to create something, right? You can notice on the side you have a browser, you have your workspace windows, you have all your tools here, and you have these buttons up here. This button hides and shows the data panel, right? This button here is the file button, which lets you save as and export as different file types. This is the save button, your undo button, your redo button, and all of your tools. This right here is your browser, right? So your browser is going to have your main component, which is your workspace. This is called, like I said, the main component or the parent component. Here are your document settings where you can change the type of unit you're going to be using. Depending on what kind of robotic system you're using, you may want to go like inches or millimeters. Most of the time you're going to be using millimeters, but if you're using Tetrix robotics tools or robotics platform by AndyMark, you're going to be using inches. You'll also be using inches for Actobotics. So here you can change what kind of system you're working in. You're gonna also have your account right here, which will give you your Fusion or Autodesk account and your preferences. In your preferences, it's going to ask you, well, how do you want Fusion 360 to behave? Most of the stuff, it doesn't matter really with how you touch it, but right here, you can just select which unit you want as your main unit for every single design. And then you can change it in the design, like from design level, if you know what I mean. This right here is the origin. When you're making custom parts, it's really useful to have the origin. The origin basically defines the three planes in which you can draw things and extrude from, including the very center of your canvas, essentially, as well as your axes. Now, this allows you to draw objects, right, and just draw objects and dimension them from certain planes. Now, you see, I kind of have an issue here. One of my tools is gone, right? And this is very important to learn before actually learning what any of the tools do, because you're going to be losing tools all the time. For some reason, Fusion just likes to troll you and remove tools from your toolbar. So if you want to go find a tool and keep it on your toolbar, you're going to find the tool in the specific section that it's in, and go down to the three dots and press pin to toolbar and pin to shortcuts, right? Now, I think it's because I'm on a smaller, yeah, it's because I'm on a smaller display right now. So this display will only fit 5, but if you get like a bigger monitor, like my left-hand monitor is, all of your toolbars will show up. So I'm actually going to hide some toolbars right now. So I'm going to hide this one. There we go. So now we're back. We have everything we need. Now, this dimension tool is extremely important, but the reason why we have origins is that we can actually dimension them to the origin. We can dimension our spaces. So you see this origin point here? We can just define, well, how far away are you? Well, you're 5 millimeters away. Or how far away are you? You're 20 millimeters away. Whatever, right? And it dimensions the part for you. Now, we kind of just skipped a few steps there, so I'm going to explain what all that was, right? So when you go into Fusion and you have your project, you can make these folders to organize inside your project. So I generally organize all my folders by 3 different sections, and I'll show you right now. If I go over to iteration 6, I have the assembly folder, the materials folder, and the subassemblies folder. Now each section deals with its own thing. For example, the assembly will handle the main assembly of the robot. All the materials for building the robot are going to be put in the materials folder because the materials folder, if you organize it correctly, you can just take that materials folder and turn it into a bill of materials to order the parts you want. That's actually how we got all of these parts, by organizing them through the materials folder. Now, the sub-assemblies folder will have all of your miniature modules. So it will have your wheel modules, your slide modules, your claw modules, what have you. And it'll have all of those modules there ready for you to just drag and drop onto the robot, right? So first things first, I'm going to go through some of these basic tools. You can't really do, like in Robotics CAD, you don't necessarily need to make any custom parts, especially if you don't have a 3D printer or CNC, you really have no reason to. But if you needed to make a custom part, then you gotta learn what all of these tools mean. So we're gonna start with Create a Sketch. This is the most important tool in your arsenal because it allows you to create a 2D shape and extrude it into 3D. So I'll just show you how that works again. So you're going to create a sketch, and then you're going to select one of the three planes, right, that you saw in the origin section. Now I'm going to select the the X plane right here. And so this is X, this is Y. Or yeah, this is X, this is Y, and then straight up and down is your Z axis. Or sometimes, depending on how you orient, you can look at this cube at the top and figure out what your planes are. So I'm at the top plane, and as you can see, I can literally just hold and drag around my cube. This gives me a bunch of different angles and views to look at my drawing. Now, on the cube, you can just select a plane to take a look at your design from the plane that you're specifying. You can also look at corners, edges, corners, all of this stuff. And you finally have the home position, which is this position right here, the corner between top, front, and right. So let's actually draw something. Here are all the tools that you're going to need to create a shape. Okay, that's why it says create. So you have text, which just looks like this, where you can define an area and just start typing away. You also have a line. The line can help you define pretty complex shapes like this, right? And now you just have a face. And of course, Control Z will undo everything. And you have your rectangle. Now each one of these sections has their own number of options, which I'll go into in a sec. So this is the circle tool. You basically define a center and also define a diameter. So it's not a radius, it's a diameter. That's very important to remember. For a spline lets you create Bezier curves. So these are special curves that follow very specific mathematical rules to create these very interesting shapes. Okay, so if you want to make a cool splotchy design, you can go ahead and use Bezier curves. You can go ahead and use splines. I generally don't use splines, however. Then finally, you have the mirror tool. The mirror tool is one of the most powerful tools in your entire arsenal, which honestly I say a lot, because you can take any number of shapes that you have drawn before, and if you just want that feature mirrored, like let's say you have two things that two symmetrical objects, and you don't want to go through the extra work of redesigning, right? Then you can easily just select your object and then select a line for it to mirror. So of course you need a line to mirror it first. So we can just extend this one out, and then you just mirror this across this line, and then bam, you have your mirrored object. Now your mirrored object is going to have this constraint, which is called a symmetry constraint. Now that will cause you to have these cool properties where everything needs to be symmetrical. Okay, So guys, in the live stream section, let me know if you're following along. If not, just let me know and I'll go over through some things. Okay, so now I'm going to get started on these modify tools. So modify is a set of tools that allow you to change the sketch object that you're using. So let's say you have a rectangle, right? And you want to make a round rectangle. Well, then you could just select these corners and specify how round you want your rectangle to be. So you can make it 15 millimeters, 20 millimeters, which of course will mess up your model. To a certain extent, you can't go really far with your fillets, or they're going to mess with, or fillets, however you want to say it, or else it's going to mess with the other shapes that are there. So you can do 5, you can do 10, not 510 because that will mess up royally. But essentially, you can just specify your radius that you want things to happen. Okay. Now you have this trim tool, right? So let's say you just made 2 shapes, but you only want to keep you only want this to be 1 shape instead of being 2 that you can manipulate independently. Well, then you can snip certain parts of the shape. For example, you can snip here, 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 and here. Now it's all 1 shape that you can change on a whim. Okay? And sometimes Fusion messes up with collisions and stuff, which will make some of the most funny errors ever. Like, there are some hilarious things that you can do in Fusion. Now that you know how this one works, you can also do something called an offset. Let's say you want to make a tube, right? And the inner diameter of this tube is 5 and the outer diameter is 6. So you can make a circle that, let's say 60, just so that we're in centimeters. It's 60 centimeters outer diameter and 50 centimeters inner diameter. But let's say you don't necessarily want to draw another 50 centimeter hole. Well, you can just offset your circle inward by negative 10 millimeters. Now you should have a 50 centimeter hole. Or no, not 10, because then you'll get you'll get 40 centimeters. So, or 40 millimeters, yeah. So you kind of have to think. You have to use math, right? I know it sucks, but you're gonna have to use math to figure out offsets because you want your offset. Your offset's gonna apply to the entire shape. So you're essentially doubling the amount of offset to affect a new shape. So like you saw before, my offset was only 10 millimeters, but the entire inner diameter changed by 20 millimeters. So because you have 10 millimeters on this side and 10 millimeters on this side that you're offsetting. Now let's say we wanted the inner diameter to be 50 like before, then we'd have to offset by 5 because 5 on this side plus 5 on this side is 10, and 10 minus 60 is 50. And now you'll have the right size pipe. Okay, from here we can actually look at scaling. Okay, so this is a sketch scale. So you want your entities, and then you can just select a point out in space by making a point using the point feature, and then that will extend your object to that point or scale your object to that point. All this stuff, there is. I'll go through that in a sec. But all this stuff is, it's meant. All Fusion is really meant for experimentation. So the reason why I know this stuff is because I figured out which tools I like using the most and selected them on my toolbar. Well, maybe not blend curve. Blend curve doesn't need to be there, but everything else is like, okay, I use this more often than any of these other features. I should keep using it. So I should attach it to my toolbar. So most of these tools, I'll be completely honest with you, I don't know much about sketch scale. I don't know much about blend curve. I don't know much about extend, but I do know about chamfer and fillet because these are the tools I use. Okay? So now we're going to get into some of the constraints. I'll show you the constraints in a sec, but we actually had a question. So Anish is asking, is there no circle by radius in Fusion? The answer is there actually is circle by radius. So you can just create a center diameter is how it starts, right? And you even though it might not be here, you can easily just do a center by radius by just doubling the radius of the circle you want, because that's the same thing as center by diameter. But the answer is no, there is not. Which is, it is what it is. Because um, and I personally think center by diameter is just superior, because you can, let's say you have a square, right? Let's say you have a square or a rectangle, and you're like, well, I want this rectangle to have a hole in it, but now you want to define the hole by like a radius instead of a diameter. Well, if you define by radius, then you can, of course, the merit of that is you can select the center of the rectangle and extend outward by that radius. But that is not necessarily relevant if you can just select the center of the rectangle by default in Fusion. So if you just select the center of the rectangle anyway, then changing the radius of the or making the radius of the circle more important than the diameter doesn't necessarily matter. So yeah. So now we're gonna go through the different ways to make shapes. So here's a 3-point rectangle, which, as you saw, it uses 3 points to create a rectangle. So that one is very self-explanatory. 2-point is what we looked at before, and then center rectangle essentially makes the diagonals for you, and you just need to select a slope from the center or from your point of origin for this rectangle to define the rectangle. Now these are construction lines, so as you'll see here, which are extremely useful in some parts of Fusion 360 that I'm not going to go into right now because they're a lot more advanced than we need to look at right now. So, so now that you understand how circles and rectangles work, we can look at arcs. So an arc basically is just a series of points that you can manipulate into a part of a circle. So if you'll see, you're going to have the center point. Well, that just shows where the center of the circle is that you have the arc originating from. Now this is useful that it shows you this, because you can easily manipulate where the arc is, but you can also determine what kind of radius you're dealing with. By the way, excuse me, sorry about that. By the way, you can actually affect or change, not even change, just look at measurements in Fusion on the bottom right hand corner. So if I had a line like this, well, I could just be like, how long is this line? Select the line, bam, there it is, it's 105 millimeters. You also have a more in-depth version of this called the measure tool, which lets you select many points and determine their distance from each other. Okay, now we're going to go back a little bit and look at the same pipe that we made before. 60 millimeters and 50 millimeters. Let's say we want to extrude this pipe. So I'm going to finish the sketch, and now I want to make this pipe. So I'm going to make it, let's say, 20 millimeters tall. So what you saw me do right there was click the extrude tool right here, and then select the region that you want to extrude. So I want to extrude the region between these two circles. And then I can go 50, 20, and I can define how tall this region will be. Okay, so now I have a ring that's this big. Okay? One more important thing that you have to know is that with Fusion 360, you can do something extremely important called dimensioning. So you have just an arbitrary circle, right? But let's say you want this circle to be a certain dimension. Well, now you can change the size of the circle by that much. Now, let's say you didn't actually want the circle to be 20 millimeters. Well, you can double click on the dimension and be like, okay, now I want it to be 30 millimeters. Okay? So this tool is very important also because you can set aside how far apart things should be from each other. So let's say let's say I have this rectangle. I want to make sure this rectangle stays the same size every time. So I'm going to select this dimension and press enter, and it's going to save the size of that dimension. Now the size of the dimension won't change. So let's say I change this. Now you just have a rectangle that's floating in space that won't change size. So now I want to make sure this rectangle is like 25 millimeters away. Wow, so now we have a rectangle that's 25 millimeters away. We can't increase or decrease the size, but we can increase and decrease the vertical size. So dimensioning is really important to make sure you're referencing things against each other. So that was extremely important with our custom parts because we had to be like, okay, so now we're in our robot and we want to make this custom part that holds up our idler bearing. Well, how do I do that? Well, I'm just going to dimension a sketch from the certain plane that I want, and I'm going to dimension it so it's a little this distance away, this distance up, this distance down, correct? And that lets me orient everything in space. The point of fully constraining a sketch is that once you have a fully constrained sketch, you know that that sketch will not change. So there have been issues with my Fusion 360 and other Fusion 360s where as soon as you finish a sketch, you may accidentally like hold and drag something and it will mess with the positioning of the sketch, right? So more often than not, it's not necessary to fully constrain a sketch, but when you want things to have an exact position relative to each other, then you're going to want to fully constrain your sketch. Okay, so does that make sense? Okay, so I'm gonna move on now. So here we go. So now we have our two shapes. Like I said, you can extrude these shapes. For the rectangle, what if you wanted to fix that point without referencing the origin? Is there a fixed constraint? Yeah, actually, so you can select this constraint and press fix or unfix. So now this shape will fix itself on this plane. So here, let me show you. It should not move now. Yeah, you see, I can't even select it to move. Now it's fixed to its position on the right and left side. And now if I want to fix this point too, now I can't even move the rectangle whatsoever. So if you want to keep things in the position they are, you don't also necessarily have to constrain. You can just fix two sides and bam, you're good, right? Of course, you can also reference things to each other. So let's say I wanted to make a line and I wanted to reference this rectangle to this line, but I want the line to be tangent to my circle. So I'm going to select the tangent tool in the constraint section and select it tangent to the circle. So now this line is just perfectly tangent to the circle. Now I can easily dimension this line to this other line and delete this so I can do that. And just change from here. So now it's this rectangle is 20 millimeters from the edge of the circle. So that's going to be very helpful learning how these constraints work. So horizontal vertical just says that a line is perfectly horizontal and another line is perfectly vertical. You can see that right here and right here. These are both horizontal and vertical constraints. Now this tangent constraint, like I said, puts a line tangent to a circle. Now let's say I wanted to make two lines the same length, right? This line is not the same length as this line. Well then I can make this line equal to this line, and now the lengths are the exact same. Okay? Now let's say I wanted to make these lines parallel. Well, I can do this and do this, but this says it's over constrained because they're already parallel. They're both vertical lines. Well, now I want to make this weird curve, this weird edge parallel. Well, then I'm going to select these two and send them to the parallel. So, as you can see, these constraints are very useful in making things work. And also, one last thing before leaving this sketch menu is that we have an extremely important series of events when you want to make something. So let's say I want to make a cube, right? Well, what shape do you need for a cube? You just need a rectangle or a square. or you need a square for a cube more specifically. But the important premise here is that you want to draw your shapes before constraining them. You want to draw your shapes before defining them, so you know what shapes you're working with. So, for example, well, now I want to make this into a square. Let's say it's 20 by 20, right? Well, that's way far away from the origin. Well, let me fix that. I'm gonna go put my thing here like this, and I'll make this constraint -10. Or not negative, I'll just make it 10. Or not even that. Let me just make it 0. Or not even that. If we make it 10 and then we constrain this one here by 10. Then, like, there you go. And then let's say you want to make 4 squares. Well, then you can make 2 lines here. This one and this one. And now you can easily just go in and mirror these. Okay, wait, let me select this last line. Now you can easily mirror this across these 2 lines. So first you mirror it here. And then you can select all these features and then mirror it here, and now you have 4 squares. Okay? So that's sketches. That's literally sketches. So I'm gonna now walk through with you how to make a very simple object, right? So let's actually change into inches. Okay, so let's change into inches. And you remember, to do that, you go to the document settings and you change active units to inches. Okay, so now let's say I want to make a 2 by 2 by 2 cube. Okay, so you guys can pause the live stream, or if you guys are watching this like in the past or in the future, where the live stream's already posted and my friend has edited all the clips and stuff, then you can of course go back and pause here and do this exercise with me. So you know how to extrude, right? So let's extrude a shape. Before we actually do the exercise, you need to know how to do this. So let's extrude a shape. You already know how to do that by changing the height of the shape. And then we can just select another plane of this object that we have here, which is called a body, by the way. Once you extrude something, it turns into a body. Now, on this body, we can make another shape. And we can now extrude this shape from the top of this body up or down. Now, as you'll notice, if you extrude down, you're going to cut into the object. That's a cut operation here. Okay? So now you have a recess by 0.4 millimeters of this rectangle. So this is going to be very important in making this cube. So now knowing how to dimension, knowing how to extrude, I want you to make a 2 by 2 cube that has a square on one side, a square on 2 opposite sides, a triangle on 2 equilateral triangle on 2 opposite sides, and circle on 2 opposite sides that are alternating between pushing out and pulling in. So once my friend edits this live stream and it goes up on my YouTube page, it's going to, of course, the final product will be there for you guys to reference. But right now I'm going to walk through with the people here how to actually go about doing that. So first we want a 2 by 2 cube. So we're gonna dimension our rectangle 2 inches by 2 inches. Okay, so now we have a 2 by 2 rectangle. And then we're going to extrude this, finish sketch, and you can either press the extrude tool or press E. So we're gonna press E and extrude this by 2 inches. Fun fact, this exact exercise was actually like a part of the Rice Robotics application to get into robotics at Rice Middle School, which was the first team that I ever joined. So this used to be part of your required knowledge. So now we have our cube, right? Well, now I want to make my equilateral triangle and things like that. Okay, so let's actually start with our square because it'll be the easiest thing. We want our square to be 1 inch by 1 inch. Well, that was easy. Now we have a 1 inch by 1 inch square. Let's dimension this quickly. 1 inch by 1 inch. There you go. Now you have a 1 inch by 1 inch square. And we can extrude this upwards by maybe not 1 inch, like 0.25, fourth of an inch. Well, that's done. Now let's make a circle that has a diameter of 1 inch. So the circle is going to, well, we can look at sketches. By the way, this will happen a lot. Let's say you want to make a sketch on something and there's a sketch that's in the way. Well, what you can do is just hide the sketch that's in the way and continue with your own sketch. So now we have a 1 inch circle, right? And we want to extrude this backwards by 0.25 inches. So we're going to select how many inches we want and go negative 0.25 inches. Well, now we have a recess of negative 0.25 inches. And then finally, let's make a triangle. Now the triangle is the hardest part because you need to first do the math, right? Because this is very much a trigonometry or a special right triangles thing, right? Because let's bring back a line now. So reset panel customization. So you're going to essentially make a line, right? So first, let's ask ourselves, how do you make an equilateral triangle? Well, an equilateral triangle is two 30, 60, 90 triangles stuck together on their longest leg. So let's make a 30, 60, 90 triangle right now and figure out what the center of that triangle is and then manipulate that triangle upwards. Okay? So first we're going to make a line. We want this line to be, or first let's actually make a line from the center. Because if you remember on a 30, 60, 90 triangle, you have one leg, which is 1, and then the hypotenuse is going to be 2. Yeah, you could also do that. That approach would work as well. But, if you want to be more exact, you can go with lines. So we have a circle, and, sorry, that's my brother, by the way. Say hi. Hi. Okay, bye-bye. He's trying to find a vacuum cleaner. Anyway, so you have your circle, right? And you said you wanted to do an inscribed polygon, or yeah, inscribed polygon. So we're gonna do this and make our circle. Now we obviously don't want it to have 6 edges, right? I mean, generally that's how many edges you'll have, but you can change it to 3. And then you can just change this to, the only issue is now you're gonna have to do the math. Because this will take the diameter of the circle that you're using. So if you'll take a look, this line right now should be, 0.9, right? So when you make your inscribed polygon, you want each edge length of your, if you want each edge length of your triangle to be equilateral, then you're gonna have to do math because it's not gonna let you just get away with telling it what the edge length will be. It's gonna tell you, it's gonna take the radius of the circle as your edge length. So then you're going to want to do 1 times the square root of 3, which is square root of 3, and then that will be the length that you put in. And we can, go through this. You can also do an edge polygon, which will just turn it into that. Now this is actually an easy approach because you could just go 0.5 away like this, and then take your edge polygon and make it 1 inch. Oh shoot. Okay. 1 inch. Where is it? Here we go. Edge polygon 1 inch, and then there we go. But you want to change it to 3? Well, there's your triangle, right? So that's actually way easier than the inscribe polygon section. But now you want to find the center, right? This is not the center of the triangle, trust me. It's gonna be it's gonna be, well, actually never mind, it is. Remember, I'm not the most goatiest to CAD persons of all time, but anyway, so we have our inscribed triangle, but we want to make this centered, right? So now we're gonna draw the center lines. And now we can just be like, oh hey, now you go right there. Bam, we're constrained. Okay. So now we can finish sketch and extrude this out by, let's say, minus 0.25 again. There you go. So now that's your cube done. Yeah, that's it. So when you go back and watch the video, whoever is going to do that, I doubt anybody will, but if you go back and watch this video, try this exercise out for yourself. Okay? So yeah, that's that in terms of making custom parts. Now we get to move on to the fun stuff. Oh, by the way, for everybody in the stream, did that make sense? Do you want me to go through anything? Do you want me to test out any other approaches? Like, just let me know right now. Oh wait. Does that make sense? All right, perfect. So now let's go and look at some really cool things. So this was our robot before our season ended. So right at states, unfortunately we didn't make it to worlds, but it is what it is. But this was one version of our robot. If you see our actual robot now, we kind of switched up the position of these servos. But right now I'm going to demonstrate to you the power of joints. Okay, joints are some of the most powerful things in Fusion 360. In Onshape, they pretty much have joints on by default. Then again, Onshape was created by SolidWorks, and SolidWorks has something called mates. Mates are essentially joints. So we use a couple of joints here. We use 2 rotation joints on the servos and rotation joints on the fixed positions on the chassis to create this kind of motion, to demonstrate this motion. Now we also used slides. We use slide joints to demonstrate the slides motion, as well as over here we use slide joints. But as you can see, actually, as the slides go up and down, they're paired with the motion of the GoBuilder motor. The motor has a revolute joint, and this joint is motion linked with all of these joints. So I'll actually go into detail on how all this works after I demonstrate how joints work and the building systems and things like that. First off, the most important thing in FTC CAD is knowing how things go together, right? So you need to have a base instinct on, okay, well, here's how Rev works. Here's how GoBuilder works. Here's how GoBuilder type things work. Here's how Rev type things work, right? So, for example, one big failure of a lot of early CADers is that they know enough about CAD. That's fine. They just don't know how things really work in the real world. Because CAD can very much skew your perceptions of how the robot should be built, how the robot should be working according to how it's built. So, for example, on this robot right here, our linkage system, the way it was right here, didn't work at all. Because in CAD, the perception was that it did based off the motion links. But in real life, like that kind of physics doesn't apply. If you want your thing to be straight up and down, you have to apply basically infinite torque to make this go, which would never work, of course. So that is really important to know for any CADers out there. Like you need to know that your CAD model may not reflect reality. That's why I generally recommend that people who know how to build, so builders, just hobbyists, learn how to CAD after they understand how the systems work. But for right now, I'll just go through quickly how things work in Rev or GoBuilder, depending on what you're using. So we're going to look at some Rev parts first. Now, what I'm pulling in is a component, right? So let's go through the hierarchy right now. What you just saw is this is the parent component, and I just inserted the child component. So one of the child components. What that means is I basically dragged and dropped, or right click and press insert into current design, another component that was already made, which are all this stuff is on Rev's website or GoBuilder's website. If you search for a part, like actually I'll just do that right now. I'll show you. So here's my alt, right? And I'm just gonna go to GoBuilder, right? And let's just say I want like a 2-hole pattern plate. Here's a two-hole pattern plate. Now I can go here and download the step file. Okay. From here, you can take your step file and press upload and drag it and drop it here. And it'll upload it into the folder that you want. From there, you can save the design you want to work in and drag it and drop it from your side menu, right? Now that we have this, I'm going to show you how things work, right? So you have your parent component, which is every single component that you have in your design. So now I've inserted another component. Well, now this component is just here, right? But it's now part of the parent component. Now, the parent component is both these components together, all right? Well, now I want to put these components together. How am I going to do that? You can press M to move or rotate a component by selecting it in the browser. And then you can change the angle at which you want to rotate it. From here, you can select a circle with the joint tool, which J is your joint tool. So when you press J in your shortcuts, you're going to get your joint tool. Now, I'm basically selecting the joint right here. And then for Rev, I can just go into the channel and select this point here. Now you see it kind of went through the model. You don't necessarily want that. So joints give you a very nice feature of being like, okay, well now you can move back a little bit and really align yourself. Now we're lined up. And I can easily turn this into a slider joint along the x-axis. There we go. So now we're sliding along the x-axis, right? So what you just saw was how Rev goes together. What you need to kind of understand is that Rev works with a series of these channels. Okay, so the screw heads of the Rev screw heads fit into those channels, and you can put different plates onto those screw heads and tighten them with nylocks. So I'm actually going to show you something pretty cool here. As part of IB, which is the school I go to, you have to do this thing called an IA for every single one of your classes. It's essentially a small research paper about a research question that you're trying to find out. For example, my physics research question was, to what extent does the angles of a joint in a two-axis arm affect the force on that arm? And of course, I use torque equations and things like that to find that force, to to use servo ratings and things like that. But in order to do this, I had to borrow a bunch of Rev parts to make this actually. So let me show you real quick. So I go into my things. Of course, I have a folder for everything that's just my stuff. So this stuff is pretty much hidden from everybody. So if you go to physics IA, test rig, this will load in just a sec, but this is the test rig that has every single one of my components on it. So what you'll see is I actually have the joints hidden, so it's not so cumbersome to look at. But I can manipulate how these joints are functioning in CAD. Okay? Now some of these joints are rigidly connected, so I can't move these two apart. Like I can change the motion of this. But if you look, I just have these plates just on the extrusion. This is called an extrusion, by the way. But I have these plates on the extrusion. So what I would do to actually build the model is put screws in through these channels and put them through into the plate, then tighten the screws. Now you have a rigid connection. So I kind of like to classify like different building systems as fixed hole systems and variable side systems. So Rev is variable side because you don't have a really fixed position where things go. Correct? You don't necessarily know. Well, this plate will go all the way on this end, but you don't know how far that's going to be. You don't have fixed holes to dictate your motion. So back to this Rev demonstration. The plate could be at any position on this channel depending on where you tighten and loosen it, which has a very good advantage of being extremely versatile. Like you can do some absolutely crazy stuff with this. For example, back in my 10th grade year, I actually built a robot that takes full advantage of how Rev works. Now, it's kind of lost a lot of its cool functionality simply because of time. Like some of my parts got deleted for space, and it started messing with my robot. You'll see in just a sec as it loads. So this was that robot, and if it wants to like do its thing, give it a sec. So 5 components are out of date. I'm not gonna update that, trust me. But I kind of tried to use Rev's full capabilities to build this robot. Now the way that this works is, um, I took different Rev parts to secure them together, um, just like this, to make sure they are at angles. Now, and you really just need to use geometry here, right? You have one plate here, you have another plate here, and these plates need to be parallel. So if you want to make one higher than the other, like in real life, then you need to use the same angled bracket to make it parallel. Now, essentially, this was a muzzle loading robot that pulled a ring up and over and then shot it out from the same side. But I tried to use Rev's fullest capabilities here. Okay, but this is really what's possible with Rev. You can make an insane number of versatile objects. Now with GoBuilda creates some of the more crazy stuff. Yeah, that is the Peshbots robot from Ultimate Goal. Um, don't tell anyone I said this, but I kind of carried in 10th grade. Um, because nobody else was gonna CAD the robot, and I was tired of being like made fun of. So I was like, okay, it's my turn to carry, and that's what happened. That robot is my pride and joy. Like that robot was fantastic. Even though it kind of sucked, it was like it was really game breaking because we didn't see any other robots that had muzzle loaded features. Everybody else was just shooting like they were picking up robots from the or rings from the back and shooting them outwards. So they would pull in like that, which was kind of bad uh because like like how are you supposed to function if the rings are rolling out the same direction that the goal is? It's like, well, then you're gonna have to spin you're gonna have to spin your robot around, pick up a thing, then spin it back, and then shoot. It's like what's the point of that? So we wanted to just make a different solution, and that's what we did. So anyway, now I'm gonna go into how GoBuilder works. So GoBuilder is a number of fixed holes. What that means is they literally take a aluminum channel and just bunch of drilled holes, right? It looks like this. I'm sorry if I sound like crazy right now. It's because I'm getting excited because like I'm the CAD guy. That's what people know me for. Anyway, you now have okay. So you can take a look at this channel. You can only have these set distances apart, which is something like I think it was like 8 millimeters apart, 4 or 8. Let's check actually. Wait, not like that. Circle, nah, bro. Circle. 8 millimeters. So each one of these holes is set off by 8 millimeters, and that's the step distance, right? That's basically how far things can go. So with GoBuilder, like, sure, it's versatile, but I don't really like it that much. Let me be honest. Even though it's like the new industry standard, it kind of secures you into a set path for how you can do things pre-built. So this is what I call pre-building. When you don't have 3D printed parts all over the place, then it's pre-built, right? But when you do have 3D printed parts all over the place, like right here, then those are custom parts. So I could never achieve a bunch of slide inserts with Misumi slides by using GoBuilder parts. That just doesn't happen, right? So GoBuilder kind of sets you into this path of how you want to, how you have to do things. Okay, so now because most people are using GoBuilder now, I'm kind of gonna demo a robot. I'm gonna demo building a robot, and you guys can just follow along. So what you'll need for this demonstration is a 10 hole. You need the files for a 10 hole U channel, or a GoBuilder 1201. So this is a quad block, right? You're gonna need any number of axles with an E clip. An E clip is here. Let me just show you. An E-clip is just this little clip that acts as a shaft collar, and this is I love this thing. It's so nice for builders because they don't need to worry about securing like bulky shaft collars all the time. So this is your E-clip, um, and yeah, there you go, the Rex E-clip. Now that will be paired with a GoBuilder shaft collar on the other end. And I forgot to insert a Sonic hub. Let me go back and do that. You're also gonna need a GoBuilder Sonic hub. So let me find one real quick. One sec. I'm getting a bunch of. So you're good. Let me find that Sonic hub for you guys real quick. Sorry, just notifying someone that I'm in the middle of this. But now we're gonna have our Sonic hub. Let's copy this. And by the way, you're gonna. I hate to be that guy, but did I learn basically everything from CAD just doing it, just literally just doing it. So a lot of this, like, oh well, how did you do that, Amit? Well, how'd you do that? How'd you do this? I honestly, it's just now like an instinctual thing, and I think that's the case for any parametric design or any like application that you use. Like for Google Docs, you never be like, oh, how do I insert an image? Well, you just copy and paste, right? So I'll try to be as vocal as I can with this stuff. So what I'm doing right now is going to the thing that I want. I'm gonna right click the component that I want and press copy. Now I'm gonna copy this component and put it in the folder that I want by double clicking the project and then double clicking the folder. So now there's a copy of that item in the folder that I'm looking at. I'm sure if you're a CAD freak like I am, then you know pretty much everything about this stuff. If not, if you're using Onshape, then I don't really know Onshape, unfortunately. So I'm gonna be asking you guys questions. Like, if you want, go in the comments and just be like, oh hey Ahmed, you're silly for using Fusion 360, and just teach me how to do Onshape, or I'll teach myself at some point. But okay, so we'll go back here, and so we're gonna insert our quad block, insert our Sonic Hub, and then we're gonna insert our um, our wheels, right? So here's our Sonic Hub. And then and then I'll do wheels later. I'll do wheels after doing motor. So also, I want to make things clear to you guys. A lot of these multi-function parts, they're multi-part parts, if that makes sense, like the motor or the shaft collar or the Sonic Hub or the axle. Actually, they come in separate parts. So if I open up here, right here, the reason why these two things are stuck together is because I've created a rigid group. So if you look at joints, I have a rigid group, right? So let's say I were to delete this rigid group, right? So like the stock part would look like this. This is how you get the part from GoBuilder. It looks like this on the browser. This is how it comes together. But look, oh no, this part is not attached. Well, how do I fix that? Right? You don't touch the part at all, and then what you can do is assemble, create a rigid group between these two components, and now they're going to be permanently stuck together. Right? Now, I advise that whenever you get a part from GoBuilder, from the GoBuilder website, and put it in a CAD, always, always, always do this, because otherwise it's going to mess with your program. You're going to have to hide a ton of stuff, and it's just a complete mess to deal with, right? So back to the GoBuilder demonstration. So I do this with every single part I get, right? I check to make sure if it's multi-part or not, and if it is, then I'll just fix it, right? So now this is how I assemble my robots, right? You guys might find it cringe. I honestly don't know. But by the way, we have bevel gears. Where are the bevel gears? That's a good question. I have no idea where they went. It's whatever. I'm gonna go through direct drive system right now. So for direct drive, you don't actually need this shaft and your axle. All you need is a motor, your Sonic Hub, your quad block, and your wheels, right? So what I mean by direct drive is you're actually gonna have a bunch of different types of robots, right? So you're gonna have H drive robots that look like this. You're gonna have X drive robots that look like that. You have C drive robots that look like that, right? You have O drives that look like that. So with all these different drives, you have different ways of driving the robot with drive, right? So you have a direct drive, which means your wheels are directly stuck to the motor, which is really good in programming, because then you're like, well, okay, my motion will not be hindered by grinding gears, slipping chains, whatever, right? So that tends to help programming a lot. But you can also use gear drives, which are just like two bevel gears. If you know how bevel gears work, then this is a very easy explanation. But basically, a bevel gear is a gear that sits like this with angled teeth. and you can sit another bevel gear on top at 90 degrees, and it translates rotational motion. Okay, so that's that kind of bevel gear drive is used a lot by a lot of teams now because you can hide your motors, which is really nice. Hiding motors is always a good deal because you save space, right? You can also do a chain drive, which is kind of frowned upon nowadays because it's kind of clunky. You could use a belt drive, which uses two teethed belt to make things go, right? Sorry. And you could also use a bunch of other wacky stuff. You could use swerve drive, which is done by barely anyone in FTC. I don't recommend it because it's really hard to do. Like only gluten free has made a really successful one that most people copy. So you could also do swerve drive, okay, which uses two differential core. It either is a direct swerve drive, which has one motor for changing like the swervy part and the other motor for driving the wheel, or you have a coaxial swerve drive, which has two motors, one that directs a top gear and the other that directs a bottom. That as it spins the motor and changes the position, or spins the wheel and changes the position of the wheel. So those are really cool, but they're really complex, and I really wouldn't recommend it right now. But okay, so let's move on. I'm kind of getting caught up here. So first of all, I want to before I do anything, I'm gonna ground my piece in space. What that means is right click your component that you want to ground and press ground. So capture position. Now this piece will not go anywhere, right? So now I'm going to move my quad block so it's in the correct position that I want it to be, and then I'm going to use the joint tool. So first I'm going to rigidly joint it so that the two parts don't move when they are put together. So think about jointing as kind of like putting a virtual screw into the part that you want to hold together, right? So now look, like this part is not going to go anywhere. And if I were to unground this, these parts are like rigidly fixed together, right? Oh, shoot. So ground, right? So now we have that. I'm going to insert my motor in here. So let's put this motor in the right position. So I'm going to select my motor, spin it around, and then select the threaded holes, and then insert them into the non-threaded holes. Here's something very important that you need to know. Do not put two threads together. I'm begging you, don't do it, because you're going to ruin the thread and you're going to ruin the part, right? So what I really mean is there's ways to attach things, right? If you've been in robotics, then you know how mechanical systems work. Like when you have a screw, if you want to attach a screw into something, you have a nut, right? Now the nut has threads in it. Oh, okay, there we go. So the nut has threads in it, but as the nut is tightened, the screw is tight. But some parts have these threads embedded in them, right? So the motor does, the quad blocks do, and that avoids a lot of like clunkiness and space wasting. It's very efficient. However, you can't put two threads together, so you can't put a nut on a quad block and then drive a screw through it because that won't work. Because the pitch between the one thread and the other will be all sorts of whacked if one is a longer distance than the other. So
I don't mean to interrupt. I've got Shrimp Theory on TV.
okay, thanks, Dad.
Say hi to your friends. And...
I'll clean up, Dad. Go away.
Okay.
Bye, Dad.
All right.
Sorry, that was my dad. So, yeah, my room, like I said, is completely messy right now. But so now what we've done is we've attached this motor in here, rigidly fixed. So at every single one of these joints, you can imagine a screw in real life going through and holding it down. Okay. So now I want to attach a sonic hub. Okay. So we have our sonic hub here, and I could just spin this around, right, to get to the position that I want. And then I can select the joint tool. Now, in order to select any one of these random points that are here, you select on the face that you want, and then you can drag, and then you can hover your mouse cursor over any of these points, and it will select a point for you. One important thing to note is that you want all of your points to be centered. So when you saw me attach the quad block to this hole here, I was finding the center of the hole of the quad block that I wanted to attach to the center of the hole of the U channel that I wanted to attach. That keeps everything very strict in its position. So make sure you remember that. Well, so now I have my rotational jointed um, uh, sonic hub, right? And you can see that I'm revoluting it. So if I were to animate, it's going to spin this way when I go to manipulate the model. Okay, now that looks wonky because you can't, if this axle is rigidly connected to its motor, then you can't really do anything about it, correct? So now we have this rotating thing. So if I revert position, now I want to attach a wheel on it, right? Well, how am I going to do that? Well, I'm going to drag in a wheel, and you also have to know something important about how these wheels work to avoid hitting screws on your robot. You have one side of the wheel that's very close to the outside and one side that's recessed. This recessed part here, you see that? You want to avoid attaching the sonic hub onto the recessed part, and instead you want to attach the sonic hub to the part that is not recessed. That will keep your wheel from hitting a bunch of screws and just not working in the real world. Remember, when you're CADing for the real world. So have what my greatest recommendation is be a builder before CAD. I swear to God, that's the best recommendation I can give. Because as a builder, if you have building experience, even a little bit of building experience, you know how things are supposed to go, right? And that's what you're trying to achieve. So as you can see, I selected the center of this hole and I attached it to the center on the quad on the Sonicon. So I changed the position to rigid, and there we go. Now we have a wheel that's stuck on a motor that's stuck to a channel, and it spins. So this is really all this jointing business is really important to learn. Okay, and then the last little bit of information that I'm going to go through. So we're going to end around like 12 or probably 1:30. I might either go to 1:30 or just 1, depending on how much time we have left, or depending on how much more material there is to cover. So first of all, now we have this, which is pretty great, right? We just now have a wheel module that's spin, right, which is very good, very cool, very nice. But now we want to build a robot, right? Well, that's only a very small step. Now you're going to have to mirror this entire operation over here. You're going to have to build a chassis. You're going to have to put 2 more wheels. You're going to have to put all your stuff. And that's really complex. That's really hard to think about, right? Especially if you're just starting off CAD without much building experience. Now, if you have building experience, you can just go like, well, I know what I need to do next. I need to put another wheel on. And I need to think about how this year's game is achieved. So back in Ultimate Goal, the game was I'll give you some context, right? The game was shooting these orange rings into these goals, these 3-tiered goals. So there's a small goal, medium goal, tall goal, and on the side of these goals there was a little chute for that's CHUT for you to drop for the human player to drop rings into that. Those go into the field. Okay, so you have to build a robot that grabs rings and shoots them into these goals. Okay, so a lot of teams tended to use the same idea of intaking from behind the robot and outtaking from the front of the robot. Okay, now this was kind of flawed because the rings were, if your robot was facing forward, the goal was also forward. So your rings weren't going behind your robot, they were going in front of your robot. So what we tried to do was think up a plan. Okay, here's what we want from our robot. We want a robot to fit within 18 by 18 inches. We wanted our robot to be within 44 pounds. We wanted our robot to intake and outtake from the same direction, and we wanted our robot to strafe. So 2 out of 3 of those things are very easy to accomplish. Strafing is very easy to accomplish by just using mechanism wheels, and being within 18 inches is very easy to accomplish in the beginning. In the beginning, that's very important to stress, right? Now, what we did after that was like, well, how do we accomplish the other 2 problems, right? Or the other problem? How do we make it where we intake and outtake from the same direction? Now, the way that we thought about this problem is, well, you could just use a conveyor belt. Like, you can just make a giant like conveyor belt that just scoops them through. And I was like, how do you do that? Like, design it, show me. But the best we got was a drawing. And then I was like, wait, why not just make like a little tower like this, like a little pyramid, and it goes up and drops. So that's what we did, and it worked really well, right? But the hard part was going, how do I turn this into CAD, right? Because of course CAD is extremely useful in building a robot. Sorry about that. Regardless, I had to work on it and think about all the different ways we could do this. So going to this season, our question was, we changed our parameters many times, which is part of the reason why we failed. But we changed our parameters many times. We went from, we want a linear slide that goes up and down, to we want a transfer that way we don't need to spin our robot every single time like a lot of other teams did, right? And then we were like, wait, but what if we just increase the intake arm so that we could just go to any like corner and just be like, oh hey, give me, and then pull back, and then transfer. And that's what we ended up with, right? We didn't have enough time to program, which is why our robot was pretty bad. But we essentially had this system here where oh, that's gonna crash my computer. Let's see what happens. But we tried to conquer the issue. How do we make an expanding intake without using belt or string? Because we had a bunch of problems with belt and string. So we're like, okay, well, I'm going to make a linkage because we saw that other teams were using linkage. We knew 12791. I think that's their team number. Iterative Intentions were using a linkage. We knew another team from the NorCal area were using a linkage, and we're like, we are inspired to use a linkage. Let's do it. And I was responsible for catting this robot, and I was like, well, what the heck do I do? So one important thing to realize is ideation. How do you solve these problems? And the only way to do it is step by step, right? So first thing I thought of was, well, I know I have to make a linkage, right? So I'll actually show you all of the iterations that I went through to get to this design. So if you go into assembly, one important thing is to look at your design history if you want to look at all the things you did. First things first, we needed slides, right? So as this opens up, I'll let you know what we did. Open recovery file. Huh? Okay, let's save this. That's not right. One sec. Let me save this just to make sure it works out correctly. So you can go back and open, or you can create a milestone for when things happen. You can, and that's good for documentation, by the way. That's very good for, oh hey, my doc guy is like, oh crap, what'd you do? When'd you do it? Why'd you do it? Well, hey, I could just show you these milestones. Exactly. Yeah, exactly. So we tried using belted. We tried using belted horizontal slides and they didn't work. We tried using stringed horizontal slides. They didn't work. And we're like, okay, I'm tired of this. So I was like, okay, let me just design a linkage. By the way, the best part of CAD is that if you have a solution and you can design it, then that solution is probably what you're going to do. Because your team needs to know what exactly they're looking at, and that's why CAD is essential. If that makes sense, right? So no, wait, I want to. Sorry, just messing around. Okay, so this was one of my older versions. So first things first, I was like, okay, first I need to make a base. So I made a base out of these three channels. This channel here, which is this one, this channel here, which is this one, and this channel here, which is this one. And I connected all of them with quad blocks. And then I was like, okay, well, that's easy. And then I was like, wait, so where am I going to put my wheels? So I knew I could direct drive these two wheels because the motors were concealed, but I knew I had to make a bearing drive here. So what did I do? I just made a bearing drive, and it's easy for me to say I just made a bearing drive. So and you have to know how things work first. For example, I know that I can only attach a motor in space with a quad block, but I also know that I can only attach a bearing to another bearing if the second bearing is on an axle. Well, I know I can only attach an axle a if I have another constraining feature, which is my sonic hub, and I know that in order to have all of this stuff, I need bearings here and here. Right, this other bearing is hidden, but you'll see you can be able to see it on the real robot. So I took all of those things and I was like, okay, how am I going to put it together? Well, this goes onto here, which goes onto here, which goes onto here. All the axle things line up. It would actually. So this was a huge problem with our thing, but all we needed to do was change how fast this wheel was driving, and it wasn't necessarily gear ratios because these are 1-to-1. These gears, it was more friction. So we had to play with the looseness and tightness of these bevel gears to work with that. So what I would recommend for any newbies, do not make a drive system that uses either bevels or direct drives. Make a drive system that uses like that doesn't combine them is what I'm trying to say. So don't have bevels and direct. Just do direct or just do bevels. Okay, that's my biggest recommendation. Now, anyway, back to it. So I figured out what I wanted to do with my chassis, and then I was like, how am I going to conceal huge slides? These SAR 230s. And then I was like, wait, they fit inside. I can stack 3 stages inside of a U channel. So that's what I did. I made 2 U channels, attached them, put the slides inside of them, figured out how to attach those slides, and that was it, right? And I made special inserts for the slides. Now everything's locked here, so I can show you on the outside edge, I think. Wait, is that not a component? Well, that's silly of me. Anyway, you can go like this and you'll be able to see how these slides work, right? They extend in and out like that. And then I was like, well, where am I going to put the linkage? So I said, well, the linkage, well, the linkage is just going to be attached to the front. And then I was like, okay, well, I wanted a turret. Where am I going to put the turret? I'm just going to use an Axon servo and put the turret right in the center of the robot. But I was like, where am I going to put the turret though? So I put a U channel between these two channels that were already here. I was like, okay, well, that's how I'm going to put the turret on. And then I was like, well, what next? I have to put the slides on. So I went back and made slides. Oh, because the front two are different. Yeah, but like, it worked, so I don't know. I think it was a programming thing at the end of the day. Because if the gear ratios are different, couldn't you just drive one set of motors more than the other? Like, or less than the other? If you're doing this, if you have a speed mechanical advantage? Regardless, that doesn't matter. So, we had to solve problem by problem. Well, not problem by problem, but like, the best ideation is to ask yourself, well, how am I going to do this? How am I going to do that? How am I going to do this? Knowing the ways that you can do it. Okay? So at some point, I was like, well, now I have to insert my slides. We had a really big thing that we need to do. We were questioning how am I going to make slides that are belted? Because we wanted Misumi slides, right? Because Misumi slides not heavy, not not slow. So we were like, well, what are we gonna do? And then I looked at the Viper slide video on how they make the Viper slides, and I was like, well, I can just copy this. I can just use how they do the Viper slide belted, and make it into a Go Build a system, and that's exactly what I did. So if you look at, I'll have to find it first. There we go. I think this is it. Yep. So first, I took the long robotics inserts from Misumi and changed them so that they would fit the larger diameter of the idler, or larger length of the idler bearings. Because of course string is so much less thick than belt, but belt is better. I mean, belt is better. I don't care. Belt is better. I will never not say belt is better. But so now I was like, well, now what? In the Go Build a Viper slide video, you have a string system or the belt system that goes up and under, and then over, under like this, right? And I needed a way to attach this backplate to the Viper slide, or to the Go Build a C channel. So that's what I did. I made a backplate, and then that elevates off the C channel base, and then you thread the belts through, and then you have a place for one side of the belt, and then a place for the other side of the belt, which is here and here. And then I was like, well, I need to be able to put my outtake on. So I made two holes here, one for the top outtake, one for the bottom. Or one for the top one for the bottom. And that's how we made it one of the most solid, like, linear actuation systems that I've ever seen. Like, this system was so nice. It like never failed. The only time it failed was putting too much stress on the belt and snapping. But that was a very easy fix because we already had slack in the system, and we just needed to reduce that slack, and that's it, right? So I would highly recommend you go with belt. But that was a huge problem we needed to solve. Hey, how do we belt Misumi slides? So we took the resources that were already there and altered them to fit our purposes. That's all CAD is. That's all you're doing with CAD. CAD has really two purposes. How do I innovate, and how do I construct? Your first goal with CAD is to construct. Just build the robot in CAD because you can do that without being on meeting time and without messing with anybody. And then your second goal is, well, we need a solution. We need it now. How do I do it? And then you build it in CAD because you have the time and you have the resources. So, yeah, that's about it, guys. Like, yeah, that's pretty much it. Nothing else to it. If you have questions, please ask. Like, do you want me to go over something? Uh, let me know. Yeah. Was the audio okay? Was the video okay? Did everybody understand everything? Just let me know how things went. Just waiting in the comments for that. This is, by the way, this is my first live stream since my Minecraft days. So it's been a. Just don't look at those. Those ones are cringe as heck. Hey, how do we build Misumi slides? So we took the resources that I realize now that like whenever I look back at the stream, it's like so much far lag behind. It's crazy. That's whatever. I'm not good at English. I just said so much far lag behind, bruh. Okay, just let me know if you guys like enjoyed it. If I should do this again. Like thoughts. Um, yeah. Let me know if you have any questions. If you had fun. If you want me to go through, I can go ahead and build a robot for you guys right here. That way you can follow along later. Actually, I'm gonna do that. I have plenty of time, so I'm gonna do that. First we're gonna go back to here. We have everything we need. So go build the parts. Right here, right here. Drag this in. And then we're going to attach this one whole offset because it's gonna just get in the way of it's just gonna get in the way of the threads if it's not offset. So here, look. So it would usually be here, but now I'm gonna offset by one hole. And now it's offset by one hole. Right? So that's not gonna get in the way of anything. And then I can bring in my even better, I should offset by an entire hole. So you can go back and edit joints actually. So you can press edit joint, change where you want this joint to be put. I'm going to change it to here. So now the joint is on a new place. And then you can drag and drop another U channel. Spin this up. Spin this to the side. And then redo. Just continue the process. So joint here. Joint here. No big deal. No muss, no fuss. Now we have one side done. Now I can do another one, and then that's a robot done. Like I just need to do the motors and stuff, and that's it. So here, 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 here. Move this 90 degrees. Joint this. Joint this to this. Attach it, or not even that hole. Joint it to this hole. Attach it. Press OK. Bring in another E channel. Even you don't even need to copy this in. You can just copy this one here and then paste. And then bam, you just have a copy. So that was just Control V, Control C, Control V for anyone who didn't know. But now I'm gonna select another joint here and here. What you have to pay attention to is that you're jointing two things that are on faces that you want to meet, right? So you don't want to join something on this face and then on the bottom face and then expect them to work. You want to join two things that you want to be on the same face. Okay? If that makes sense. So now I'm going to insert another set of these. Here, here, these quad blocks. I realize now that like I'm not really talking while I'm doing this. I think it's because when I'm doing CAD, I tend to just like be silent instead of like talking out loud what I want to do because a lot of it is repetitive and after a while it just becomes instinct. So what I'd recommend for any newbie CAD members is literally just start experimenting, right? Start building stuff just for the fun of it, and then you'll really easily learn how things go together, right? You don't necessarily need me to teach. I just need. All I need to be there is for like questioning. You know what I mean? Everything else is an exploratory process. So here, so I'm gonna copy this grounded feature, bring that out, and then that's pretty much the base done. Now all we need to do is attach the wheels, and then we're good to go. And by the way, in CAD, here's my mortal like enemy. I have no idea how mechanism wheels are supposed to go. Like you guys can clown me for that. Like I've never learned if it's like X on top or O underneath or O on top X underneath. I honestly don't know, right? And if you don't know what I mean by that, like ask on the FTC Discord, which honestly I might do right now. Question: when I do a mechanism drive, are the wheels supposed to form an X on top or on the bottom? Okay, there we go. I'll ask in the chat. Mechanism wheels are supposed to go. Like you guys can clown me for that. Like I've never learned if it's like X on top or O underneath or O on top X underneath. I honestly don't know, right? And if you don't know what I mean by that, like ask on the FTC Discord, which honestly I might do right now. Question: when I do a mechanism drive, okay, supposed to, regardless, I'm just gonna continue. I can just change the wheels later. That doesn't matter. So anyway, so we have this, right? Oh, come on, man. Silly Billy. Honestly, I can just copy this and paste it. Okay, gotcha. So if you're following along, guys, I doubt you are like anybody in the live stream right now, but if anybody encounters the videos, then please feel free to follow along. Like this stuff is, it's really good practice, right? So we have our mechanism wheel. We have, why do I, okay. Now we're just gonna copy this motor assembly everywhere else. I mean, I'm not even gonna show that because it's kind of a waste of time because we've reached time just about. So, you know, feel free to subscribe if you want to. I don't really care, but yeah, this has been a pretty good live stream. Let me know in my Discord, by the way, I'll put it in somewhere. But like, feel free to DM or ask me questions on the FTC Discord. My name is usually Amjack or Amit on either of these Discords. Please just ask questions. I'm free most times, and by the way, I'm by no means the best CAD person like ever. I'm just a guy who likes CADing and who knows a little bit about it. So yeah, thanks everybody for watching. It's been a lot of fun. Yeah, Hemant to go on God on H. All right, see you guys.